Found this article in the New York Times about scientists measuring the forces that are involved to push a single atom across a surface. And in this article, they talk about how different atoms being pushed across the surface of platinum require different forces. So, for example, to push a cobalt atom across a smooth, flat piece of platinum, the force is 1/130 millionth of an ounce. And to push a copper atom is a little bit easier. It's 1/1600 millionth of an ounce of force. So I thought we'd use this idea to look at how we can calculate an angle involved in doing work. So let's take a look at that. So let's assume that this force we know is we're going to look at copper. And that is a force of 1/1600 millionth of an ounce. And so we then need to convert that to force. And I looked up on Google what the conversion between force and in newtons and ounces is. So 1 ounce is equal to 0.278 newtons. And so if I convert this force, I will get F equals 1 divided by 1600 times 10 to the 6 times that. So this is in ounces, and I need to convert this many newtons per ounce, and so the force will be approximately 1.7 times 10 to the minus 10 newtons. Now that force is along the direction in this diagram. I'm going to redraw the diagram, so let me just choose some colors to match. So this is copper, and we have this surface of platinum, and we're going to apply a force to push that looks like this, and then that copper atom is going to move along the platinum surface along delta R. And in this case, delta R is, we can call that delta X because it's along the horizontal surface. And so what we would expect is that the force has components along X and Y, and the motion of the copper atom is going to be along X. And so we know that the work involved here is equal to the force dotted. I have a real tendency to want to use a D instead of a delta. The force dotted with the change in position, both of those as a vector, and once we take the dot product, they become a scalar. And we can rewrite that as the magnitude of the force times the magnitude of the change in position times, make some space, so we can write that as the magnitude of the force times the magnitude of the displacement times the cosine of the angle, and in this case the angle is this. And so when we take that dot product, what we're calculating is the projection of F onto delta R, so that if I were to draw these two vectors like this, what we're looking at is how much of F shadows along delta R. That's the idea of the dot product. Okay, so let's assume that we know what the vector for the force looks like. And so we can then write down that vector. Let's say F has the form where there's an x component that is 8.69 times 10 to the minus 11 newtons. There's a y component that is 1.50 times 10 to the minus 10 newtons, and no z component. And similarly, we can write delta r. We're going to assume that that's all along the x direction, and so we need to figure out what that looks like. But we already know that if it's along the x direction, that this looks like a number in the x coordinate position and then 0, 0. So platinum, let's just think about a particular example. Platinum has what's known as a cubic structure that looks something like this. And the spacing between two atoms is 3.92 times 10 to the minus 10 meters. We have another way of writing that. That's 3.92 angstrom. Just another unit that we use, named for a physicist. So let's assume that we want to take this copper atom, and we're going to start here and then move it so that it goes 1, 2, 3, 4 spacings of the platinum. So that would be 4 times 3.92 angstrom, and so then we could write that delta x is 4 times 3.92 angstrom. And if we do that math, then we know what the delta R is. And that delta R is going to be 15.7 times 10 to the minus 10 meters. And so we now have enough information that we can write down the dot product to calculate the work. And we also have enough information to write down the magnitude of each of these vectors, but we don't know the angle. So let's just take each piece here. Let's start with this dot product here. That's going to be 8.69 times 10 to the minus 11 newtons, 1.5 times 10 to the minus 10 newtons, 0 multiplied by 15.7 times 10 to the minus 10, 0, 0. And so I'll have only a multiplication of the x's. The others are going to be zeros because 1.5 times 0 and 0 times 0 are both 0. So this will be so when I multiply those together, I get 1.36 times 10 to the minus 19 joules. Next, I know the magnitudes of these two vectors, and so I can calculate this. If I didn't already know these magnitudes, I know from up here, since I know what the vectors look like, I know from up here and here, I could calculate the magnitudes of those vectors if I didn't already know the magnitudes, because I could just use the Pythagorean theorem to calculate those. But I know when I only have one component of a vector like delta r, that the magnitude is the size of that one component. And then f, we know from what was given to us in that article. So f was 1.7 times 10 to the minus 10 newtons. And we're going to multiply that by this distance, 15.7. And when I calculate that, I will get 2.7 times 10 to the minus 19. And that has units of joules as well. So you can see that the magnitudes of the two vectors is larger than the size of the dot product of the vectors, and that's because we're going to have to multiply by cosine of theta for these two magnitudes, and cosine of theta goes between minus 1 and 1, and so that indicates that we're going to make this number that's in red smaller simply because we're going to multiply by some number that can't be any larger than 1. Okay, so let's think about what we're going to do. We started with this. And so what I'm going to do is just move things around because I want to know what theta is. And so I'm going to solve for cosine of theta. That just looks like the dot product divided by the product of the two magnitudes. We know what those two numbers are. So we have 1.36 times 10 to the minus 19 joules divided by 2.7 times 10 to the minus 19 joules. Very important that the units here are the same because cosine is a function that is unitless. And so we'll get cosine of theta is equal to 0.5. There are some decimals there, but we haven't been careful to keep up with lots of significant figures, so I'm going to assume that I only have one significant digit here. I can then take the arc cosine of both sides, which is just asking the question, where does cosine equal to 0.5? And that's true when theta is equal to 60 degrees.